Hello, my name is Will Spoth, and today I will be giving a talk on reducing ambiguity in JSON schema discovery. JSON is primarily a data exchange format and is stored either directly as text, as a binary format, or in a columnar format like Parquet. A JSON dataset is simply a set of rows that happen to be JSON records, and tools like MongoDB, Postgres, Oracle, and Apache Spark enable storage and retrieval of JSON data. You may be asking yourself, why JSON datasets? Isn't that inefficient? Well, JSON is a convenient way to serve data to external third parties. The specs built-in data types, nesting, arrays, and transportability make JSON a top choice for developers. Let's use a silly example. Say you're Twitter, and you have a public API so that third-party applications are able to integrate with your website. Then one day after a poll, Twitter decides to rebrand itself to the equally cute name Kidder and adopts a cat mascot. Doing so, they decide to rename Tweet to a meow and to update their API accordingly. If you're the Twitter API developer, this is as simple as editing a string and no need for a formal schema update or migration script. It's scary to think it's that easy. Schemas help us reason about our data. They tell us what types and columns it contains, and encapsulates a logical grouping of related fields. To generate a JSON schema, most tools like Apache Spark simply take the union of all row-wise schemas and escalate their types. However, the schema it produces is unable to discern if a row, in this case, should contain a meow, a tweet, both, neither, or some combination in between. Beyond just a column renaming, assume we have records generated by two separate processes. Our Spark extractor will simply union all rows together and will output a single schema. As the creator of this toy dataset, I argue that it makes more sense instead to output two schemas, one built just from business records and the other from user rows. Digging through datasets, we noticed another trend, where developers like to embed key value pairs in rows. Here we have drug names as JSON keys and prescription counts as values. Same as before, Spark will generate a single schema and treat this embedded pivot table as any other set of attributes. A more ideal extractor would tag this RX object as unlike a standard JSON object. Detecting and correcting these abnormal structures and partitionings are the main focus of my talk today. The last pivot table example is a case of what we call structural ambiguity. We point out two main violations of our intuition. First, objects should contain some optional fields, but not into the thousands with an overwhelming amount of nulls. Additionally, if we think about the kinds of processes like direct I/O of JavaScript maps, it is unsurprising all keys share the same data type. We also notice the inverse of this pattern, where arrays are used as unlabeled tuples. This is characterized as a fixed size array, potentially with mixed types. Unfortunately, we see this even as part of the GeoJSON spec, as well as in log and configuration files. We detect when a structure is behaving in a manner that would make it hard to reason about. A good gauge to ask is, how would I load this into a database? Then we attempt to detect partitioning opportunities. This allows us to produce a set of schemas that individually better represents the data. It's worth mentioning that JSON datasets can be quite large, both in attribute size and row size. So it is important to choose a metric that is both memory and computationally efficient. For efficiency, we limit ourselves to only consider attribute occurrences and types. After testing various metrics, we settled on using a fairly popular entropy formulation as our measurement of volatility. We define key space variations using our entropy formula, with the probability of a key occurring within an object, or size for arrays. This metric then maps variability to an interval from 0 being fixed and increasing with volatility. We define a similar computation for types, using the probability a type occurs in a row structure, then averaging across all rows. These metrics allow us to define a new JSON structure, which we call a collection type, creating a handy metric to find objects with volatile key spaces and stable types. For our experimental datasets, it was as simple as setting the key space threshold to an arbitrary value of 1 and type threshold to 0. This simple rule was enough to identify all objects, which we later manually determined to be collections. Now let's look at some different ways a JSON schema can be generated. As mentioned, we could simply union all the rows together, which we call our flat extractor. This is the de facto extractor of choice and is used by Apache Spark and many other systems and prior works. Second, we could partition every distinct row schema. We call this our verbose extractor. While this, according to our definition, reduces ambiguity, it is largely useless, leading to tens or even hundreds of thousands of schema entities. Ideally, we want an extractor that is capable of nuance, grouping similar schemas together while partitioning dissimilar rows. And if you're thinking what I'm thinking, then this is a job for clustering, which is what we did. First, we generate a set of ground truths by using the flat extraction technique just on the partition subset of the data. Our Yelp dataset came pre-partitioned as 6 individual files. Our ground truth is then generated by performing flat extraction on each individual file. We are then synthetically comparing our extractors run over the whole unpartitioned dataset against individual file schemas. Our GitHub ground truth was retrieved through a single HTTP endpoint. 14 events can be recovered through an enumerable field indicating the event type and processing in the same manner. For evaluation, we take the minimum symmetric difference between the set of schemas output from each extractor versus the set of ground truth schemas. This metric matches the closest possible schema while still penalizing over and underfitting. To create clusters, we generate binary feature vectors out of the data, again based only on attribute occurrence, not on attribute value. Not surprisingly, the flat extractor produces schemas that don't closely match any particular ground truth schema, greatly underfitting. Interestingly, standard clustering techniques like k-means seems to detect a few schemas, but struggles to recover all ground truth schemas. We see this continue even after manual tuning and with different distance metrics. What's more surprising, perhaps, is that clustering techniques expected to perform better at this task, such as hierarchical clustering, seem to do no better than k-means. After doing some testing, we realized the large difference in expressiveness was skewing our distance metrics. In this example, we use an arguably better suited metric for binary comparison, Jacquard similarity. Large, highly optional business records are contrasted by small and stable photo records. Using the formula for Jacquard similarity, in this example, we see photo record 1 is most similar to business record 2. Even more so than business record 1 is similar to business record 2. And this exact pattern is what we see in our synthetic Yelp dataset. Large, highly variable business events that share a join key with small, stable photo events. Likewise, Euclidean distance and cosine distance encounter similar problems, and from testing, this isn't a problem that can be fixed by regularizing by multiplicity or some other biasing function. So, to reiterate, our extractor choices thus far are between a flat extractor that fits every row but no particular row, this being the current de facto extraction technique, a verbose extractor that produces tens of thousands of possible schemas, overfitting our data, or a clustering technique that has the ability to partition schemas into a manageable group size, but experimentally misses the mark due to the skew caused by large entity discrepancies and the sparse information provided through binary feature vectors alone. But I'm here talking today, so you might be able to guess we found a fourth option. After doing some background research, fields like bioinformatics and document clustering have run into this problem before. Bioinformatics frequently attempts to extract this block-like structure that we noticed in our data Bioinformatics has found success solving this problem using a technique called biclustering, where columns and rows are grouped simultaneously. Unfortunately, many of these biclustering techniques are specifically tuned to bioinformatics and proved too niche. However, we dug into some fundamental algorithms and drew inspiration. We started with a straightforward biclustering technique, a benchmark algorithm called BIMAX. BIMAX starts by performing iterative pairwise set comparison between two distinct row schemas. The initial grouping aligns with many of our best assumptions of JSON's schema relationships, namely the assumption that rows which are subsets participate in the same underlying schema, while both disjoint and combined sets need to incorporate more information. Next, we apply a merge step that takes this assumption one step further, attempting to reconstruct this subset relationship out of a smaller, likely incomplete schemas. Our merge algorithm is a bottom-up, greedy iterative algorithm that attempts to combine various smaller partial rows to recreate larger, more comprehensive rows. It does so by ordering first by smallest schemas, then attempting to incrementally build a larger target schema using only smaller partial rows. If a larger, more comprehensive schema can be recreated, it constructs and adds that schema, ideally bringing along additional attributes to form a more complete schema picture. This continues until no new schemas can be formed through this combinatorial process, and all targets have been iterated through. The remaining schema sets then become our entity candidates, and this process is applied separately and recursively to embedded arrays of objects. We find BIMAX merge perfectly recovers our Yelp ground truth schemas from our synthetically merged Yelp dataset, as well as recovering the 10 unique GitHub schemas which do not participate in a complete subset relationship with another schema. As an added bonus, we'd like to point out our algorithm requires no thresholds, tuning, or K parameters, although there is room to incorporate some of these for performance tuning. In our experiments, we also evaluate a naive BIMAX approach to verify our merge step is adding value. In the real world, ground truth datasets are few and far between. Some datasets contain enumerable attributes or come as separate files, but most do not. To be able to compare with more datasets, we created 3 metrics to quantify how well a schema describes a dataset. First and most important, we test recall, or the ability of a schema to generalize to a dataset. We test schemas produced by 1, 10, 50, and 90% intervals against a 10% validation set. A schema with low recall has little practical use, so when interpreting these results, this is our primary metric. Second, we define schema-level entropy or ambiguity. This is the total number of possible distinct rows which a schema would validate. For example, the schema produced from our Twitter Kidder example produces 4 possibilities from a single column renaming. Intuitively, the more possible worlds that the schema can occupy, the more ambiguous it is, which has implications for schema discovery as well as false positives. Finally, grouping is simply the number of entities within an output schema. We want this number to be as low as possible while providing the highest recall and the lowest ambiguity. This is critical for any user-facing capabilities, generalizations, and is indicative of over-partitioning. These metrics enable us to expand our experiment to 13 datasets, 12 being real-world datasets and 1 synthetic Yelp merged dataset. As expected, we found the flat extractor had high recall since it tends towards generalization, but also high ambiguity due to its high use of optional fields. We found the verbose extractor to have low ambiguity, but at the cost of unusably low recall and immensely high number of entities. Finally, we found our BIMAX merge algorithm to have equal or negligibly lower recall compared to the flat extractor, while having orders of magnitude lower ambiguity. Additionally, we validated the importance of our merge step drastically reducing the number of entities, as well as improving convergence, in most cases plateauing between 1 and 10% training size. In this paper, we introduced the various causes and ramifications of schema ambiguity. We present and use entropy to detect and tag various structural inconsistencies that could better inform the user. We dive into the shortcomings of current extraction techniques to reduce this ambiguity and how they even worsen ambiguity in many cases. We outline how more common clustering techniques fail to produce ideal results and the reasoning behind it. We introduce our novel Bimax algorithm and directly compare its performance to other extractors, as well as the naive version of itself. Finally, we develop 3 metrics to determine a schema's ability to characterize a dataset, requiring no ground truth. Finally, we would like to thank Oracle for supporting this research, and I'm happy to take any questions. Thank you.